All right, so welcome back. Sorry that I was a little bit late. I was in a meeting that took a little bit longer than it should have been. So my apologies. All right, so today we want to first finish some additional discussion on out of order execution. And then if we have time, we're gonna start talking about caches. Happy election day, right? Let's see what happens. Two things relevant to you guys is, in addition to if you can vote or if you want to vote, go and go vote if you didn't already. Other than that is don't forget about your homework and computer assignment too, okay? So your homework is due, I think, on Sunday, and the computer assignment is due following Friday. For the homework, for question 1, I think it's more straightforward. For question 2, the out of order one, we gave you like the PPT file that you can edit. Make sure that you're not, just consider you cannot edit and add more rows to your reservation station or ROB or add more registers and all. These are fixed. What you can add is more cycles, okay? So that's the only thing you can add, but feel free to add that. The second thing is that if your processor needs to be stalled, okay, out of order processor typically works this way, that you have a fetch, okay, and then you have the decode, okay. Usually there is a pipeline register in between them. There is what we call an instruction queue, okay. So since this is, for example, a superscalar processor, the fetch go and grabs 2 instructions. I'm going to put them into the instruction queue, okay? And then the decode decodes this and dispatch this and so on and so forth. If we need to stall, we typically let the fetch go and keep fetching things and putting it into the instruction queue. From the instruction queue, then we decode and put it into the reservation station. So for example, if your reservation station is full and you can only decode 1 instruction, your decode will be stalled, but your fetch can continue. For now, for this homework assignment, for example, you can assume that your instruction fetch is infinite. But at some point, your instruction fetch might also get filled. And in that case, you have to also stall fetch. So it's slightly different than what you have in in-order processors where you stall both fetch and decode together. In out of order, typically you let fetch go. And there's additional details that we didn't talk about in this class yet, and that is like usually the fetch goes through the instruction cache and bring things. And that's why you want to have instruction fetch just moving forward. So and for the purpose of your homework and your quizzes and all, if you need to stall, assume that your fetch can continue, unless we explicitly say that, for example, your fetch needs to be stalled as well, okay? And again, if you're out of your free registers or you're out of the rows in the ROB and or reservation station, you have to stall the decode part, and you have to wait until hopefully an instruction either completes or instruction retired. Then you can push new things into the dispatch unit and issue queue and so on and so forth. Yes. You start at decode, not rename. Good question. Yes, in our case, you start at rename. Yes. Mm-hmm. Yes, you always start at, yeah. Mm-hmm. Mm-hmm. So you stall it, right? So you wait at the rename. Yeah. So in reality, typically decode itself, typically many systems divide decode into rename and dispatch. So there is no decode per se. Decode itself is called rename and dispatch. So when you're stalling, you're really stalling the first part of the decode. In the terminology we use in the class, we had like a decode stage and then we had a rename stage. So you can assume that the decode can continue and then you stall at the rename stage. Mm-hmm. There was another question here, or are we good? Okay. And then the computer assignments, I saw some people started working on it. it should be like the baseline design should be simple. You should be able to improve the baseline design fairly easily by probably just adding a few things. So I'm assuming that to get like the full grade, you shouldn't spend too much time. It should be a fairly small project. But the project is designed such that you can spend more time on it if you want to. So if you're curious and interested, if you want to get more points, you kind of like, you didn't do well in your CA or your quiz one or whatever, you want to get more points, then this is the opportunity for you to do a little bit more work. And we gave you a little bit of pointers as well. I think the discussion sections will also discuss a little bit more about branch predictors. So feel free to watch and kind of like learn more about branch prediction and design something more interesting. Any questions about any of the, yeah.
Based on your past, it's like
So the question is like, what is the maximum one can get? So as I said, there are works that one can like. There are works that shows that kind of like a theoretical limit. Actually, you can write a code that always predict correctly. So if your branch predictor kind of like goes once, let's say you have a vision of going to the future. Okay, if you can go to the future and profile the application and see all the branches and store that sequence, okay, and you print that sequence, and then each time you see the branch, you let's say you have an infinite memory of all the branches. You always can predict that. That will give you the best branch predictor. Okay, so you can actually measure that. The first time you cannot, but afterwards you can, right? So there you can find the limits if you want to, but that's not what we want you to do. We want you to have an actual branch predictor. Yeah. It's also depends on the imp, right? So that's why it's workload dependent. That's why when we provide the numbers, you see that we want you to report the average number. You will see that for some benchmarks, your branch predictor does better. For some, they don't. That's because of the patterns. So there are patterns that it's easy for the branch predictor to predict, and there are some patterns that it doesn't. Okay. Okay, so let's talk about out of order execution. So last time we discussed three main things. We discussed how we kind of keep track of things being ready using reservation station. We talked about how to fix hazards and new hazards using renaming. And then we also talked about mechanism for recovery. In this lecture, I want to give you a little bit more details of each different stage and some decisions, design decisions, because what I showed you in the last time in the class was just one way of designing out of order. There are actually other ways, and there are some design decisions, some trade-offs that one can do. So we're going to cover that a little bit, okay? So the main parts of an out of order, kind of new parts of an out of order compared to what we had for in order was we kind of broke down the decode to a new thing called dispatch and rename. We introduced the concept of retiring and using reorder buffers. We talked about scheduling and being able to schedule things out of order using reservation stations. I talked about having multiple functional units and the notion of what we call complete versus retire. So these are just kind of the new concepts that we went over last time. Okay, so let's talk about the design challenges. So first of all, I'm going to talk a little bit about different design choices, as I said. Then I'm going to talk about forwarding and flushing. And then lastly, I'm going to talk about new issues that's going to be created as a result of out of order that we didn't have or know about. And we're going to finish the discussions. So the first thing that many microarchitectures use is this notion of we have an ROB and we have a reservation stations, right? And then I told you that we have functional units in between that kind of works this way. And then kind of the ROB updates things here, okay? This is what we call a distributed design, where we have a separate reservation station and a separate ROB. Many designs actually combine these two together, okay? It's called like a centralized ROB design. So the idea is that I can use ROB as a reservation station as well, okay? I just need to add a little bit, few more columns, and my ROB would be more than enough to keep track of everything, okay? Because it kind of seems redundant that having both reservation station and ROB. So many designs, including many modern systems, combine the two together so that they have what they call the centralized ROB design, okay? Uh, uh, what is the kind of the trade-off between these two is when you combine them, your design becomes a little bit more simplified. But on the other hand, there will be more stress on the ROB because every single cycle there are multiple things needs to be read off of it. There are multiple things needs to be updated and so on and so forth. So your ROB could potentially becomes a bottleneck. It needs a lot of ports. So it becomes a very, very complex design and very high-powered design. But on the other hand, it will simplify lots of wiring. So you kind of get rid of many of the wirings between here and here because now both of them are essentially just one big ROB. So your decoder basically writes things to your ROB, and everything there from here, you basically kind of execute things to your functional units and then write the results back to the ROB. So ROB like maintains everything until the instructions becomes retired. So there will be more ports go in and out to the ROB, but you get rid of the reservation stations completely. So that's one design that many systems have. Just keep that in mind. The second thing is that we have what we call a unified scheduling queue versus a distributed scheduling queue. What we showed in the class was that we can have the reservation station, right? And then I have, let's say, for example, 3 functional units. I told you that in reservation stations, we're going to have a column called FU number that we put the number here, right? So, and then, for example, if it's 0, it goes here. If it's 1, goes here. If it's 2, goes here, right? This is what we call a centralized reservation station. And then if you combine it with a centralized ROB, your ROB would be centralized, okay? So this is one option. The other option that you can have is that you can have a reservation station, but then you can have queues per functional unit. So if this is your functional unit 1, and this is functional unit 2, and this is functional unit 3, you can, instead of having a centralized reservation station, you completely get rid of this, and you actually write things directly into a dedicated queue for each functional unit. So you know exactly which functional unit this instruction is going to use. Instead of writing it to a centralized reservation station, write it to a dedicated functional unit, okay? Again, why this would be a good idea? Because this will help you, again, simplify the design. Now you have functional units dedicated to each one. Your wiring becomes simpler. Your scheduling becomes simpler. Because now for scheduling, all the functional unit needs to do is going through this queue. And you can do this in parallel, right? So this one can be in parallel with this one and this one. So for systems with many, many functional units, maybe it's a good idea to have these separate ones. But why this would be a bad idea? Because you're not using all the spaces the most efficiently, right? Because of this isolation between these functional units, there are some functional units that may not be utilized as much as the others, right? So if I have like a unified reservation stations, I can basically find the first empty row and put my instruction here versus here. If for any reason this one is full, then I cannot put things here because, for example, if this has to be scheduled to functional unit 2, I cannot change it, right? So again, it's a difference between whether you shared all your resources versus if you dedicated to the individual function units. But of course, there are you can use more sophisticated algorithms to do the scheduling better. For example, if you do some form of a round robin, timing of a round robin, then hopefully you have the best utilizations among all your functional units. But just keep in mind that you have these trade-offs. Questions? Okay. Another thing that we need to think about, and this is again commonly, there are two options commonly used in different microarchitectures, is when is the time for us to read the data? If you remember in the class, we said that we're going to rename and use a physical registers, okay? So we're going to put things into the reservation stations, but we're not going to store the values. We're going to just put the register names, okay? This is typically called what we call read after issue, which means that, you know, the instruction is fetched and then decoded and then renamed, and then we put it into the dispatch, right? And then in dispatch, we just put instructions into the reservation station. This is our reservation station. And then we, for example, say P1 and P2, okay? We just put the register names, okay? And then when we want to issue this into the functional units, at this point, we're going to actually read the physical register file and put the data here, read the actual data here, and then use the functional units, okay? Because I know the register numbers. Whenever I want to issue them, I just read the values and put it there, okay? This is what we call read after issue. Once the instruction becomes issued, then you actually read it from the register file. And this is what we call non-data capture. I'm going to show you why it's what is the data capture and why it's not non-data capture. But the alternative solution to this would have been that instead of reading it at this point, I can read it during the rename stage. But essentially, when I'm doing the renaming, I go to my register file and read the values. And instead of putting the numbers, I put the actual values here. Okay? This is what we call read before issue or data capture. Okay? So what is the difference and why we have these two options? The reason that this is important is that it changes your renaming algorithm and it also will change your forwarding algorithm. Okay? So what we discussed in the class was this method, the first method, that we're going to use a register alias table and we're going to use physical registers, right? So I told you that forget about architectural registers. Whenever you see an architectural register, you immediately translate it into a physical register. From now on, you have a physical register file and you can move on with that, okay? That was the idea that we discussed in the class. But the alternative option to this is using some form of a tag system that you still have your kind of architectural register file, but for each architectural register file, you issue a tag, okay? So instead of having like P1, P2, P3, you can think about like tag 1, tag 2, tag 3, and essentially you kind of propagate these tags and propagate the values with each tag, okay? And then if you need to update, instead of propagating the numbers and writing it to the register file, you propagate these tags. Let me show you a picture. So this is the difference between the two options, okay? What we discussed in the class was this option on the left. This is what we call explicit renaming, which means that we fetch, we put it into some cube, then we decode and rename. If you remember during the dispatch, we put things into the ROB and we put things into the reservation station, okay? And here we use tags, but these tags were actual physical numbers. So it was like P1, P2, and so on. When we issue, we actually read it from the physical registers and then we put it into the functional registers, okay? That's what we discussed in the class. The alternative option would have been that when I'm doing the dispatching, I put everything into my ROB and I read things from my register file and put the actual data into my issue reservation station or issue window. And then if I need to update anything, then I'll just propagate these tags. The tags could be the same P1, P2, P3. It could be anything else. You just create a tag system. So if I want to update, I'll say that instead of saying that, oh, P1 needs to be updated, I'll say tag XYZ needs to be updated, okay? But the difference is that the reads already happen. So when I issue, I immediately issue, okay? I no longer need to pay one more cycle for register file read. But then the drawback of this is that now I need to store the value in my reservation station as well. In this case, my reservation station was rather small because I didn't need to store the value. But now I also need to read the register file during my dispatch, and the instruction might be there for a very long time, and the value is just there. So I'm wasting a little bit more time and power when I'm doing this. Versus in the explicit case, I just read the register file whenever I need to. I don't need to store things. I don't need to duplicate numbers in this case. In this case, I kind of duplicate numbers because I have it here. I also have it here. Yes? Yes, I'm going to show you the data capture just in the next slide, so you'll see what does it mean for data capture. Yes. Yeah, so the questions are, yeah, so these are all registers. So think about that. You have kind of another column of registers in your reservation stations that you can store the values. So the question is, why are we doing it? No. So remember, don't think about memory. This is nothing to do with memory. These are actual registers that you use, like X1, X2, X3. Remember that when you decode an instruction, then you had the reservation station that you put things here, right? So you had like P1 and P2 and so on. Whenever the instruction was ready to go, we issue this instruction to your functional units, okay? So we get rid of it and we put it into the functional units, okay? What we are suggesting, like the difference between this option and this option is that in this option, which we call explicit renaming, what we discussed last time and gave you an example, I don't store the corresponding value of P1 and P2 in my reservation station. I just store the name. So it's saying, okay, this instruction going to use P1 and P2 as their resources, as their RS1 and RS2. Okay, that's all. When I actually issue it, now I need to go and grab the actual value because P1 is, there's a number for it, P2, there's a number for it. That's when I actually go and read from the register file. So as you can see, my issue window, I only have the operations and their corresponding tags or PC or whatever, but then I'm going to actually read it from the physical register file. And then from there, I'm going to actually then pass it through the function again. So there's an additional middle step between when we are reading it from the register, from the reservation station to the when they actually executing it. Okay. In this case, I'm saying that I don't want to wait for one cycle to read from the register file. What I want to do is that whenever I put these instructions in my reservation stations, I want to also put the value. So I put the value of P1 here. And I put the value of P2 here, okay? So not only I store the registers, I store the values of them, okay? And how do I do that? I actually read the register file during the process of dispatch. So I do extra things beforehand. So I kind of prepare myself that whenever this instruction is ready to go, I have the values, I have everything that I need, I just pass this through the functional units. So that's why I no longer need to go back to the register file and read it. But what is the trade-off? The trade-off is that now I need to store values. And that's an extra overhead in terms of area and power. Exactly. We're preemptively reading during the dispatch stage versus during the issue stage. Exactly. We have to add extra registers, not memory, registers for this. This is called implicit. So we implicitly rename, right? Okay, so what has this to do with capturing and not capturing? Remember that I told you that whenever instructions in the reservation station, not all the sources might be ready, right? So there will be cases that your reservation station instruction needs to sleep or need to wait for previous instructions. So for example, in your homework, you will see that there's a load instruction. It takes 4 cycles for the load to finish. When the load has finished, then there are some dependent instructions that needs to be now issued. So in other words, we call them wake up. We need to wake them up and say that, oh, look, your data is ready. You're now ready to go to the functional units, okay? So depending on where we read the data, our wake up strategy will be different, right? So in the first case, in this implicit case where we read it from the register file first and put it into the reservation station, versus in the case that we read it, we put things into the reservation station and then read it from the register file. This is implicit versus explicit. The wake up logic and the forwarding logic will be different, okay? So when we have everything in our reservation station, that we have this case here, that we first read and put everything into the reservation station, things are nice and easy because forwarding and wake up and everything happens to the reservation station, right? So if the data is available, we put it there, we wake it up, and we read the data, okay? This is what we call data capture because the data is captured in the reservation station, okay? Um, but if the register file read happens after the instruction is issued, then we need to wake things up in the reservation station. We need to tell the reservation station, oh, look, your data is now ready. But when we are actually reading the data, we need to forward it to our register file because register file happens after we issue the instruction. So if I forward it to here, then it will be overwritten by my register file. So the forwarding happens to the register file. So essentially, we're replacing the register file by the value forwarded by the complete stage, but the wake up happens to my reservation station, okay? This is why we call it non-data capture, because we don't capture the data. We just tell the reservation station to wake up and issue, but we actually capture data from the register file, okay? And of course, when we are done, in this case, don't forget that you also need to update the register for future instructions. So the kind of two things happens at the same time, versus in this case, you can do both things at the same time. So again, there is another trade-off, which is like an additional communication needs to be happening. So which one is better? Again, really depends. There's no clear winner in any of these cases. There are different trade-offs for each one, such as, again, here, things are slightly simpler to implement in terms of complexity, but then it means that everything, there needs to be more port going to your reservation station, right? Versus here, things are kind of distributed, so simplified hardware design in this case, but much more complex algorithm for wake up, because you need to wake up and send things to reservation station. You also need to forward to your register file. So there's kind of like these trade-offs between them. And again, there are lots of modern processors that use this approach. There are some others that use this approach. So there's no, as I said, there's no like one way of doing this. There's more of a design decision that you have, okay? And so this is kind of like just summarizing what I just said. So essentially the question of read after issue or read before issue is where should I store the data, right? If I store the tags and values all together, I have one option. They have to have a bigger reservation station. If I put the data also into the reservation station, then I have a bigger reservation station, right? So sorry, the first case is that I don't read the values from the reservation station, and that's what we covered in the class. But the other option would be that not only I store the tags, I also store the values with it, which means that I have bigger reservation stations, okay? And then again, that means that when do we forward, we can either forward from complete to the register file directly, or I can forward it from complete stage to the register file. Another thing that you need to keep in mind is that when do we do the forwarding? In the class, I said that we should forward when the instruction is complete, right? Because that gives us the most performance. But the problem with when we forward incomplete is that if you made a mistake, then there are lots of more things that we need to recover, right? Because we let lots of things to be forwarded and all. We might update the register file and all that thing. An easier solution would have been that we don't forward until we retire. But remember, that means that things will be much, much, much slower. So we typically don't do this. We almost always do this. But that means that now I need a mechanism for recovering things, okay? How do I do that? I'm going to use this kind of methodology, okay? So either I can do what we call a log-based strategy, or I can do what we call a checkpoint strategy, okay? So log-based strategy means that whatever I do, I also store my logs, okay? So for example, for rat, if you remember, not only I had my mapping between physical and architectural, I also stored the older mapping. You remember we had the old register? So we kind of stored the logs. So whatever we do, we also store the previous things for that, okay? And for every register, we can do that too, okay? The second option, which is usually a faster option, is a checkpoint-based strategy. So whenever I reach to a branch, I'm going to create a checkpoint, okay, because that's where things can go, can become problematic. And instead of having one register file or having one rat, I'm going to have multiple of these, okay? So let's say, for example, I can support 4 level of branches, okay? Or let's say start with actually 2, okay? Let's say I have 2 sets, which means that I have what we call a messy set, and then I have a safe set, okay? So I don't have one register file, I have 2 register files, one messy and one safe, okay? So here's what I'm going to do. That whenever things are not retired, I'm going to write it to the messy, okay? And then when things are retired, I'm copying things from messy to the safe. If I need to recover, I just get rid of the messy and I just revert back to my safe, okay? So in this case, then I don't need to be worried about anything at all. I just have a true copy of things. I always have a correct copy. Think about it as your GitHub repo, that you have a nice commit and then you start changing things. If things goes back, you always revert back to your commit, okay? That's exactly the same idea that you have in your system. But that means that you have to now copy things twice. All your memories needs to be twice, which is coming up with like a large overhead. The alternative to this is that I only keep log of certain things, right? So then I, for example, log my rat or part of my register file and so on and so forth, okay? So these are the 2 options. Going back to the recovery, this is not just one thing you need to do for recovery. There's actually multiple other steps that you need. So what are those steps? So if you remember, I told you that whenever we decide that we need to flush or recover, we need to flush things from the reservation stations. All the instructions that are after that instruction needs to be flushed out of the reservation station. I also need to remove them from the ROB. So everything below the head of the ROB that needs to be flushed will be invalidated. Then I need to restore my RAT. Remember, either I had a copy of my RAT that I can quickly copy, or I have the old destination registers that I can revert back to it. Then I need to also free those destination registers that I did after this, right? So again, I need to basically put those that needs to be flushed back into my free pool. Otherwise, they're going to be, kind of missed forever. I also need to free my functional units, those that are inside the functional units that needs to be flushed. I just need to remove them from the functional units and make the functional units ready again. And of course, I need to update the PC to the correct PC that I need to use, right? So these are the steps that I need to take. And as I said, I can either do a log-based approach, where I keep log of things after every single cycle, or typically another faster way, but a little bit more expensive, is that I have copy of things. So I always just copy from the messy one to the safe one when an instruction is committed, right? So when things are safe, I just move it back to the safe one, okay? And then otherwise, I can just discard the messy and then just use the safe and then move forward, right? So that's the simple one. But of course, the trade-off would be performance versus extra area and extra power and extra computation that is needed. Most modern systems has some form of these checkpointing, but keep in mind that the number of checkpoints is also limited. So you cannot have infinite number of checkpoints, because you need to know how many copy of register files that you can maintain. So there is also at some point you need to stop, and you can no longer copy things over. You need to wait until things retire, and then you can continue. Okay? Questions here? Okay. All right, and then let's revisit the hazards. So there are these older hazards that we had. So for example, we had raw data hazard. And if you remember, my reservation station and the ready bits that we had kind of take care of it, right? So if there are registers that are dependent on prior registers, we use the ready bits to kind of keep track of it. And then we had this forwarding and wake up logic to update them. So that's good. For control hazards, I just described how do we fix it. We kind of have a mechanism for recovery. So we do the speculation. We assume that the branch might be taken or not taken. We continue. If we made a mistake, there is a mechanism for it for us to recover, right? So we need to do all these steps that I just described. And then if I have structural hazards such as my ROB gets full, my reservation stations get full, my free registers get full and all that, we stall different parts of the processor. Sometimes we stall the whole processor, sometimes we just stall the rename, sometimes we stall both fetch, and so on and so forth. So all the ready bits that we had and it helps us to kind of decide where to stall the processor, okay? Now the question is that does out-of-order execution create new hazards? And unfortunately, the answer to that is yes. A big hazard that is created by out-of-order execution is what we call memory hazards or memory dependencies. So if you remember, we talked about raw and write after write and write after read for registers. But keep in mind that the same problem exists for memory, right? So if I'm reading from an address before writing to that address has been finished, we're going to have what we call a memory raw data hazard, right? So for example, if I have store word x to, I don't know, 4x0, and then I have load word x to 4x0, you will see that this is writing to this address, which is address equal to 4. It's writing this value, whatever it is. Let's actually change this to x3 maybe. Okay, so this is writing the value of x3 to address 4. This one is reading from 4 and writing it to x2. Okay. So in other words, x2 should get the value of x3 in this case, right? But if I execute this out of order, which means that if I run the load before the store, because for out of order I can reorder things, right? So if I run load before store, then the value that x2 gonna get is the older value that's stored in this address, okay? And who knows what that now number is. So we're gonna have the same problem with raw data hazards for the memory as well. So we have to be very careful when we are reordering instructions for memory. And then the same thing happens for write after write and write after read, right? And remember, renaming is not helpful here because this is addresses. I cannot rename addresses. I can only rename registers. And keep in mind that if I rename this x3 to something else, this problem exists, okay? So renaming is not going to help you with memory hazards because memory hazards is because of the same addresses, not because of the same registers. So I need to find another solution for memory, okay? So I need to keep track of like the order of memories, and we need to make sure that this order is kind of maintained, okay? How do we fix that? And as I said, renaming not going to work, so keep that in mind. And as I said, this is an example that I'm giving you. So we're going to use what we call store queues, okay? Store queues in actually, I'm going to show you in the next slide that is usually combined with load as well. So load store queues, LS queues, is a queue that lets you help you to maintain the order of instructions that's been written to the memory, okay? So think about it as similar to the ROB. What it does is that instead of directly writing things to the memory, you write things to the load store queue, okay? And when it wants to be written to the memory, it only writes things to the memory when the instruction has been retired, okay? So here's what we're going to have is that if my things in the past was directly writing things to the mem, now I write things to this queue, a store queue, and this store queue will write things to the memory. But when do we write things from here to here is when that instruction is already been retired. So basically we're going to get a signal from the ROB. The ROB says that this instruction is retired. When it's retired, then we write it to the load store queue. So why do we do that? Because this decouples my pipeline from my memory, because my pipeline can move forward. Remember that not at any of these stages I stop the memory from moving forward. But when the write needs to be, so I can still run things, I can run things out of order. But when I'm actually comes to the point that I want to write things, then I write them in order. So that will fix two of these three issues that I'm going to have. It's going to fix this write after write and write after read problem. It's not going to fix my read after write problem, because it's still, if I read load before store, I'm going to read an incorrect value. So how do I fix that? I'm going to fix that using the load store queue. So essentially the idea would be that whenever I want to load something, I first check my store queue, okay? If the store queue, if the data is there, then I'm going to read it from there, okay? So here's going to be my kind of updated structure, okay? So whenever I want to write something, I write it to that store queue first, okay? Whenever I want to load something, I first go and check my store queue, because if there is a recent store, it will be there even before that's in the memory. If it's not there, then it's safe to go and grab it from the memory, okay? So this will fix my raw data hazard problem, because if I do the reordering, I can still find the value from my store queues, okay? So just keep that in mind, that if your store hasn't been finished, if you go to the memory and read that value, you're going to read an incorrect value. But if you're reading from the store queue, and then if your store queue is always following the program order, in other words, we only let the load goes if the previous instruction is retired, then I'm going to always read the correct value from my store queue, okay? So that's kind of like the way that we're going to fix this. So we're going to let things to be reordered, but when we're actually reading values, it's going to be based on the program order. And we're going to maintain this order within this, what we call load store queue. Okay? Any questions here? Good. So just again, to repeat, if I have a load or store, the first thing I'm going to do is that updating or looking for it in the load store queue. If it's there, then I'm going to read that value. In other words, load store queue forward value to me instead of going all the way to the memory, right? If it's not there, then I can actually go to the memory and bring it, because it means that there is no previous instructions that write to that address, okay? And of course, this load store queue can also get full. If it gets full, then we need to stall the processor. Same story as the others, okay? Uh, yeah. And there's one final thing, and I'm not going to describe the solution for this, but this is also a very big thing in out-of-order execution. And that is what we call memory ambiguation, and a solution for it is what we call memory disambiguation, okay? So here's the problem. So take a look at this kind of example here. I have load, I'm not using ISA, RISC-V ISA notation, I'm just using some random rotation. So I have read from R6, okay? So whatever address R6 is pointing to, I'm going to read the value of that and put it into R3, okay? Then I'm going to do R3 added with some other register and store it in R7, okay? Then I'm going to store the value of R4 in R7, the address that R7 is pointing to, okay? Then I'm going to doing some form of a sub or R type operation R1, and then I'm going to store I'm going to load R8 from R1. Okay, so far so good. So if you look at this example, you see that this seems to be a fairly straightforward example. There's nothing weird about this. But consider these two scenarios. When R1 and R7 are not the same addresses, then the order of these things does not matter, right? Doesn't matter whether I do this first and then do this next or not. But if R1 and R7 are indeed the same value, then what we store in that address this directly impact this, right? So I need to make sure that these things cannot be reordered. Okay? This is what we call memory ambiguation, because depending on the value of R1 and R7, these two stores, these two registers may or may not be dependent to each other. Okay? And because in this case, essentially what happens is that R8 should get the value of R4, but in some other cases, R8 shouldn't get the value of R4. So it's a completely separate address. Okay? And the problem with this is that I don't know that I don't know whether or not these two things are the same or not until I actually know the value of this and this. So by looking at this code, I have no idea whether these two are dependent or not dependent, okay? And I can run this multiple times, and sometimes they might be dependent, and sometimes they may not be dependent. Again, it depends on the values, okay? And this is what we call memory ambiguation, because it's ambiguous whether or not I have a dependency here or not. And another thing that makes things worse is these two first instructions. So as you can see here, you might say that, okay, why don't we quickly check R7 and R1 and see whether these two values are the same. So now look at this kind of like, the tricky part of this example is this, that R7 itself is dependent on R3, and R3 is dependent on R6, and reading it from the memory, okay? So the value of R7 itself is dependent on another address in the memory, okay? So if I don't know that value, I have to wait for that instruction to come out, for that value to come out, and now we can decide whether R7 is equal to R1. In other words, I need for load word, this load word, first load word, to complete before I make a decision about these two guys, right? Why? Because R7 is dependent on the load that depends on R6, and then R7 and R1 dependent to each other, may or may not dependent to each other, okay? So that's why, so the first solution for this problem is we're going to say that, okay, we're going to stall here because I don't know about R7. We're going to wait for value of R7 to be known, which means that I need to wait for this load to finish. And that takes many, many cycles. But I'm going to install everything afterwards. I'm not going to do anything until I know whether R7 and R1 are the same. If they're not the same, I continue. If they're the same, I'm going to issue some form of in-order processing or whatever, okay? Another option that many processor does is what they call memory disambiguation, which means that I'm going to speculatively predict that whether or not these values are going to be the same or not, okay? So I'm going to just blindly, not blindly, but kind of blindly speculate that. I'm going to say that, okay, I have a feeling that R7 and R1 are not the same. Then I'm going to just continue this normally. So I'm going to assume that these two are not dependent to each other, and I'm going to execute things. At some point, I'm going to realize that I made a mistake, then I need to recover. But the great thing about this is that I never stall my processor. I never need to wait for this guy to come, because this might take many, many cycles to come. And trust me, there are lots of these scenarios in modern systems, unfortunately. So memory disambiguation is actually a very, very common and very complicated solution for this. And we're going to use some form of prediction, similar to the way that we predict branches, but this is value prediction, so it's slightly more complex than what we had before. But we're gonna, if we can somehow predict that whether or not R1 and R7 gonna be the same value, then we can continue our system. I don't provide solution for this, but keep in mind that there are a whole bunch of things exist for the memory disambiguation as well. Okay. So the last thing I want to show you before finishing the out of order execution is that I want to show you a real example. This is what is called a boom processor. So this is a RISC-V based processor. Okay, this is a real processor. There's actually like hardware taped out for this. As you can see, it's kind of like all of these things we have covered in the class. So there is what we call a front end, which has the fetch and decode. So as you can see, there is an instruction memory or instruction cache here. For now, don't worry about these things. We haven't talked about it yet. We are fetching 4 instructions at a time. Okay, so this is a 4-issue processor. Then we put it into some form of a fetch buffer. Okay, that's the buffer that we put between the fetch and decode. And then I'm going to decode 4 wide, right? Because we fetch 4, we technically can do 4 together. And then I'm going to put it into the reorder buffer. As you can see here, we have 128 entries in my reorder buffer. Okay. And then I'm going to have a scheduler or reservation station. For this particular case, you see that it's a distributed scheduler, which means that every functional unit has its own queue, right? So we have an int queue, have a memory queue, and we have a floating point queue, okay? And then I have tons and tons of execution units or functional units. You see that I have like 3 ALUs, I have 4 FPUs, I have AGUs, branch, mul, div, store, a bunch of different things. Each one is for a particular operations. So like, you know, modern systems has many of these different, each one for different things. Yes? I don't know, they use execution units instead of functional units, but yeah, the same thing. Maybe they don't want FU, I don't know. But yeah, it's the same thing. And as you can see, we have physical registers. So this is the one that you read after issue, okay? And as you can see that there is a floating point register file and there is an integer physical register file. So typically for modern systems that support both physical as floating and integer, you have separate register file for each one. You see that there is 128 of these registers there. You also see the number of entries for these queues, right? So we have 32, 32, 32, but my reorder buffer is typically bigger because I need to maintain all of these together. And then we have the kind of the complete stage. I have my load queue. I have my store buffer, 32, 32. And later, actually this week, we're going to start talking about my caches. So I'm going to have a cache here. I'm going to have another cache here. So these would be my memory system. I'm going to the caches. We still haven't discussed this, but later we're going to discuss that. And then also in the fetch, you will see that we have a BTB. We have a branch predictor, we have a return stack address, all those things that we discussed in the class as well. You see that they're all there, okay? I think I have one more picture. Yeah, so this is kind of like similar data path controller logic that you see in the class for this boom processor. As you can see, hopefully you can understand almost all of it. So you see an instruction memory, instruction cache here. You have your BTB here. You have your branch predictor here. You have your buffer here. For these modern systems, since the branch predictor is fairly complex, you'll see that fetch is not just one cycle, it's multiple cycles. The reason for it is that the branch predictor takes more cycles. This is, of course, a trade-off because now you spend more time for fetch, but the good thing that comes out of this is that if your branch predictor is more accurate, you're going to save a lot of more time. So there is a trade-off between how complex and how well your branch predictor is versus how long your fetch takes. but you always go with a better branch predictor because better branch predictors can significantly improve your IPC, okay? So keep that in mind. Then I have my decode rename logic. I have my ROB. I have my head of the ROB and all those stuff. I have my dispatch. As I said, I have distributed queues. I have my physical registers. So this is, as I said, read after issue. Then I have my functional units, and then this functional units goes back to these registers. I haven't shown it yet, but they go back to those, okay? And then I have my load store queue somewhere here as well that goes to my memory, all right? And finally, this would be the timeline. There are 3 versions of booms. So the one that I showed you is boom version 3. This picture also shows you the previous one. The one that we discussed right now is this one. So as you see, there are 4 fetch states. There is a queue. There is a decode, dispatch. Then there is like an issue, register read. There's an extra cycle for register read, and then there's an execution stage, okay? And there is a write back, and there is, in case if there is a branch misprediction, you might go back. Otherwise, you don't pay this. The write back and then goes back. So you might have like a total of 12 cycles in this case to finish an instruction. These other ones, this TLB, decache, this is for memory. For memory, you need to do the address translation, which we're going to talk about later. So this would be for your memory. And if you have some form of an accelerator, for example, if you have like a machine learning accelerator or a GPU, essentially what happens is that at this point is when you actually invoke the accelerator. So your execution basically takes more time. And then at some point you will have your write back data and you write back the data and go there. Okay, so it's kind of like the 3 options that you're gonna have. Okay, any questions? You can also search and read a little bit more about Boom if you're interested. All right, so to summarize, we talked about like very advanced topics. So these things that I discussed today is kind of like things that are happening in real world systems. So you should be very proud of yourself now that you know lots of new challenges. So this is like literally, it's not like an ancient things that I talked to you about. This is actually happening in real world systems. One last thing is that if you want to know about these things, especially like how do we do better branch prediction, disambiguation, different types of execution units, and so on and so forth, I'll also teach an advanced computer architecture course in spring. It's a grad class, but typically many undergrads also take it. So if you want to learn more about that, consider taking that. There's also advanced computer architecture class, which is taught next quarter in winter. I'm not teaching it, but it's also a very great class if you want to learn more about computer architecture, especially these topics. Okay? Great. So that's it for out of order. Let's have a quick break, and we're going to switch gear and talk about cache. Okay? Cool. Recording continue. All right. So as I said, we want to switch gears. So we talked a lot about processor design. We start from like a bare bone design, and we keep adding and adding and adding and adding lots of things to it. And as I said, processors has been around for 30 plus years, and performance has always been a very, very important metric. That's why we keep adding these features. And what happened was that since we were able to pack more transistors, these features kind of came out cheap, right? So you can add more registers with minimal cost in terms of power and area. That's why we were able to make these processors more and more complex. But as I said, we kind of like reaching to the end of it. So really, if you look into the last few years, and if you remember that kind of graph that I showed you at week 1, that the speed of the processor kind of like flattening. I mean, it's going up like 2-3%, but really that's it. We really don't have any more things that we can add. We really kind of reach to the point at which that our branch predictors are the best. Our algorithms for all these other techniques for speculations, we basically kind of did all the possible speculations that we can. And we really kind of like reaching to the limits in terms of things that we can do in the processor, okay? Doesn't mean that kind of this stops. There's still innovation, new techniques, new branch predictors, new other things that people do. But it's slowing down significantly. Like 20 years ago, this was very, very fertile environment for like doing various different research, but it's not. The micro architecture part of it. There are tons of other things in computer architectures that's very interesting, and there are lots of research going on it. But the micro architecture of the processor really is very mature at this point, okay? But there are many other things that you need to also think about, because at the end of the day, computer system is a system with multiple components. It's not just the processor that you need to make it fast. The surrounding needs to be also fast. And that's the main thing, is the memory, because remember, all of these things that we process in the processor needs to be read from the memory and needs to be written back to the memory, right? And so far, we kind of abstracted away the memory and told you that, you know what, the memory is always there. There's always one cycle for you to go and read things from the memory. The reality, though, is that memory is a big, big, big challenge, okay? And we need to discuss the problems there that we have and how do we fix them, okay? So this is the story of what we call memory hierarchy. There's different types of memory. When we say memory, there's actually many, many different types of memory that we have, different architectures that we use, and then collectively that creates what we call a memory hierarchy, okay? So like this is the slides that I showed you way, way back that showed you that any system has basically 4 components. It has a CPU, and inside the CPU you have a data path and controller. But then you also have memory, you have inputs, and you have outputs. So this is a classic von Neumann model, okay? So for now, we've focused only on this part. Let's actually start focusing on these other 3 components in our system, okay? The main thing about memory was that, unfortunately, as we make processor faster and faster, memory fell behind. And this is refers to as what we call a memory wall. So if you look at this picture, you will see that generally we observed about 60% per year, or 100, or double every 2 years kind of thing for processor due to the Moore's law. But this thing didn't happen for the memory because the technology that we used for memory was different, and all those microarchitecture techniques such as out of order or branch prediction and all that things doesn't apply to the memory. Memory is basically this very dumb thing that you provide an address, it gives you the data. That's all it does, right? So there is not much optimization that you can do for memory. As a result, although memory gets faster, and the reason that it got faster is because we managed to have newer technology and newer transistors and newer readers and newer analog logic and so on, the speed at which that the memory gets faster was significantly slower than the CPUs. There's kind of like around 50% grows gap between the CPU and memory. And unfortunately now we have CPUs that blazing fast, but memory are very, very slow, okay? And this is refers to as memory wall. So essentially, at some point, doesn't matter how fast your CPU is, you're going to be bottlenecked by the memory. And that's really what we're seeing now. So for example, we have the capability of multiplying and summing and adding lots of numbers on the CPU side. So in theory, we can run really large, let's say, machine learning kernels and large language models and all those things on the CPU. But what really limiting us is how fast we can read things off of the memory and write things to the memory. So the speed of our quote-unquote accelerators these days is really limited by how fast we can read and write from the memory, okay? So how do we fix this problem? And the problem that we have is generally memory is this either or option. So memory is either large or either fast. Unfortunately, we cannot have both. And again, if you remember, I told you that we have different types of technologies for memory. The fastest memory that we have are registers. So essentially, our register files or some form of a memory, right? And it was really fast. You can access it with one cycle. But the problem with registers, which is like flip-flops or latches in terms of circuits, is that they are very expensive in terms of power consumptions and in terms of area. You need tens of registers for storing just one bit. For those of you familiar with the circuit design of a flip-flop, you probably remember that there are many registers, many transistors to just store one bit, okay? So I cannot have like a massive register file to store lots of data because this is very power hungry, okay? So instead what I do is that I use other technologies to store more data, but as I store more data, unfortunately it gets slower and slower. So the first thing that I use is for my what we call cache, I'm going to use what we call SRAM. So SRAM is this technology that uses roughly 6 transistors for storing 1 bit of data. So it's kind of like better than tens of transistors, but still still very expensive. And the speed of reading and writing to SRAM is much slower, unfortunately, than registers. It's much better than the rest of the memory hierarchy, but it's still quite slow. Then if you want to kind of like go for density and store a lot of data, then we do DRAM, which is usually just 1 transistor or 2 transistors, depending on how you want to count the capacitor. But unfortunately, DRAM is much slower than SRAM and registers. And finally, you can store terabytes of data into other technologies such as this technology. But then the problem with disk is that it's much slower than the rest. Another thing that this will give you is non-volatility. So that's also a big thing that you get from the disk versus all these other guys are all volatile, which means that if you restart your system, your data is wiped out versus your disk always retains the data. So it doesn't need electricity to store things, which is very helpful, right? So all of us has hard drives to store things. Otherwise, it doesn't use, it's meaningless to use computers if you you cannot store data indefinitely, okay? So to kind of like summarize the previous slides, if you compare size versus speed, you will have something like this where your register file is usually in order of few kilobytes. Remember, like for example, you have 32 registers, each one 32-bit. So we have few kilobytes of data that we can store inside the processor. But the good thing about the register file is that the access time is 1 cycle. So we're talking about less than 1 nanosecond of speed of reading register file. Then we go to the SRAM. We typically, sizes of the SRAM is few hundreds of kilobytes, 32 kilobytes, 256 kilobytes, 1 gigabytes. That's the order. But the access time is typically ranging from 2 to 10 cycles. Typically for SRAM, as the size grows, the read time also grows, okay? So that's why it's not like just one single number. For bigger SRAMs, the time it takes to read goes higher, okay? Then we have DRAM, and DRAM is typically in order of gigabytes. That's what you buy when you buy your computer. It says that, okay, it has 16 gigabytes of memory or has 24 gigabytes of memory. That's the number that they're referring to. They're not referring to this DRAM number. And the access time of DRAM is usually in order of hundreds, close to thousands, okay? So pay attention to these numbers, right? So from register file to DRAM, we are 2 order of magnitude or even 3 order of magnitude slower. That's how big the difference is, okay? So if I, for example, want to read from my register file or from my CPU, if I read things from register file, I get it within 1 cycle. But if I need to go all the way down to DRAM, I need to wait 1,000 cycles to get this data back. So now you understand how big of a difference it is. So far, we didn't talk about this at all. We just always say that your data is always within the register file or within your SRAM. That's why at best, for example, in your homework, we say that 4 cycles. But reality is that many times you need to actually go to DRAM. And even worse, disk latency is tens of thousands of cycles. That's why it takes a lot of time for you to turn on your computers. Okay, it usually takes a few seconds or close to a minute sometimes if it's a slower system. That's why, because it needs to read everything from that disk thing, right? So it takes a lot of time to read that. But the good thing is, as I said, you can store terabytes of data. So you see order of magnitude jump from, let's say, kilobytes, many order of magnitude jumps from kilobytes. And also, as I said, it gives you non-volatility, which is also huge. Yeah. Milliseconds. This number? Yeah, milliseconds. Yeah. No, milliseconds, 10 milliseconds.
No, it would not be like
Millions of cycles, of course. Yeah. So reading from this takes millions of cycles. So you see that it takes not million, yeah, almost like it takes around 100,000 cycles to read one data from your disk. Horrible. So nanoseconds is 10 to the power of 9, milliseconds in 10 to the power of 3, right? So yeah, so it's 10 to the power of 6, a million, almost million, yeah. This is also kind of like I'm assuming like 1 gigahertz of the clock. So yeah, I would say, yeah, maybe this number should be a little bit higher. Just the order I want to give you. Okay, so based on this, you will see that memory can be either large or fast. But what we want to have is both, right? So we want both large and fast. So now the question of a computer architect is, how do you build something based on these available technologies to kind of hide the delays, okay? That's what we want to achieve. And that's the idea of memory hierarchy, okay? So when we say memory in a modern systems, we're not going to talk about just one memory. We're going to talk about the hierarchy of memories that we're going to have. And the hierarchies will look like this, that we start with the smaller memory and we gradually make it larger, okay? But as we're going down, the time for things to access takes more time, okay? So this way, hopefully, if we always access from here, we're going to have this illusion that we have a memory as big as of the sum of these, but they only have the latency of this guy here, which is one or few cycles, okay? So how hierarchy would work? This is an example that the book is using, I use, and many other people use, is I consider data as books, okay? So hierarchy works this way, and this is how the analogy goes to caches and memories. Think about this, is that you have a table, you have a library behind you, you have some books stored in the garage of your home, and you have some books in the Powell library, okay? So you have these 4 different options, okay? How would you store your books? You're going to do this, right? So this is intuitive solutions for this problem. You're going to use the books that you're going to use the most on your table, right? So if you have a midterm of computer architecture, you put the book, the reference book of the computer architecture right on your table. But your table has limited space, right? So you cannot store all of your books there. You can store maybe 1 or 2. So you're going to decide what you're going to put in your disk, okay? So you're going to put two books maybe that you're going to use a lot today, and you're going to put it there, okay? Then you have the library, and maybe you store some of the books that you're going to use also in near future in the library. The other books that you're not going to read, and you see that, oh, there's been like 2 years that's the last time I saw this book or read this book or used this book, you're probably going to box them and put it into your garage, right? And then the books that you very, very rarely going to use, you maybe never going to use, or you're going to read it and you're done with it, you're going to just ship them off. You're going to use a library, a public library. You're going to go there and ask for that book. It will take 2 hours maybe for you to access that book, but you eventually will get it. But it's not going to be something that you're going to use a lot. This is the same strategy that we're going to use for data storage. The data that we need a lot, we put it into the register file, right? That's our registers. Then the data that we're going to use more often, we're going to put it in our what we call cache, okay? And cache itself has levels, okay? So there's not one cache. There's level 1 cache and level 2 cache, sometimes level 3 cache. So we're going to think, the more I'm going to use it, the closer it's going to be to me, okay? And me in this case becomes the processor, okay? And then as you can see, this will give you the illusion that you have everything you need. And if most of the time, if 99% of the time, I really just use those 2 books that I have in my table, then I'm not going to notice the latency it takes for me to go to the library, because this happens every once in a while, right? So on average, if I measure the time for me to access the book that I want, if most of the time I just use either the books on the table or worst case the books behind me in the library, then the average time would be really, really low. Even though it might take hours and hours for me to go to the library. If I go to the library frequently, then the average would be terrible, right? So that's the idea of memory hierarchy, okay? So I put things close to me based on how fast and how frequent I want to use them, okay? And as I said, frequently used books would be close. Less frequently used books would be far away. Okay? But as I said, we're still going to use books, all the books. So it's not like I have access to any book that I want in the world. Just the question is, how fast can I access it? All right? So that's also important, that you don't lose access to things. It just might take more time for you to access them. Okay? So why this would work and why hierarchy is generally like commonly used and fix this issue. We kind of talked about this when we were talking about branch target buffers. That's the idea of locality, that your behavior is predictive and based on smaller subset, which means that at any given time, you only need a very small subset of data. Again, in the book analogy, at any given time, you probably need 2 or 3 books. You're not going to read 50 different books at any given point, right? So programs also behave very similarly. It always works on a very small portion of data at any given time. So the only question is that, can I kind of switch between these portions quickly enough? Can I predict the behavior accurate enough? And if I can, then I have a really, really fast system. Okay? So again, the reason that this would work is locality. If I don't use locality, which means that I read 1 page of this book, then I read another page of another book, and another book, and another book, and another book, this will not help me. Not only it will not help me, it actually makes things significantly slower, because now I need to search. Now I need to first search here, I need to search my library, I need to go to the garage. If I didn't have this hierarchy and I always know that things are in the library, whatever book I need, I will just always go to the library and read it. But as I said, in reality, we're going to have a lots of locality in our systems. And as I told you, there is 2 types of locality. There's temporal locality, then there's spatial locality. Temporal means that in very short period of time, I'm going to reuse the same thing, which means in this analogy, I'm going to use the same book. Okay? If I'm using the same book over and over and over, I'm using temporal locality. The spatial locality says that if I'm using this book, it's very likely I'm going to use the book next to it. And next has different meanings. In data, next means next address. So think about an array. That if I use A0, I'm going to use A1 and A2 and A3 and so on and so forth in futures, right? So I'm going to, if I have an array and I'm accessing this, it's very likely that at some point I need to also access A1. And this A1 will be probably very near future. Okay? And this is what we call spatial locality. That spatially, things that are closer to each other in memory going to be accessed together very soon, in a very short period of time. Okay? So as I said, this will give us what we call memory hierarchy, that we have multiple layers of memory. Memory 1, memory 2, memory 3, and so on and so forth. Okay? So how does exactly this work? So let's start talking about details. So this is what we're going to have in our system. So we're going to have the CPU, Within CPU, we're going to have registers. So registers is really part of the CPU. They're not really a separate modules outside the CPU. They're literally, designed within the chip. Then I'm going to have caches, okay? Sometimes I use caches like this, but generally this is what we call cache. So cache is closest memory structure to my CPU, okay? Typically, I have separate cache for instruction and data. The reason for it is the locality pattern that I see for my data is very different than the locality pattern that I see for my instruction. For my instruction, I expect lots of spatial locality, but much less temporal locality, right? If I run one instruction, very unlikely that I go back to that instruction unless it's a branch or something. Versus for data, there might be lots of temporal locality combined with spatial locality. That's why we typically have two separate units for cache and data. But when it comes to the main memory and disk, they are combined. There is no separate main memory for instruction or for data. Everything is combined. But typically for cache, we're going to have separate instruction cache and a data cache. Okay? So when we're searching in the cache, there are two things that can happen, right? Either we search for the data in the cache and the data is there. When it's there, we call it this is a cache hit, okay? If we search the cache and the data is not there, we're going to call it a cache miss. If a miss happens in the cache, I need to go one layer lower. For example, if I have only one level of cache, then if it's a cache miss, that means that I need to access memory, okay? But keep in mind that not everything is also stored in the memory. Some things might be stored in the disk, okay? Next week, we're going to talk about main memory as well. And there you will see that we're going to have a miss in the main memory as well. So we eventually go to the disk. We're not going to have miss in the disk, okay? Because all the addresses that you have will be there. But you might have data has been stale or deleted and all those things. So you're going to have problems there. But like the bottom layer of your memory hierarchy would be this. So everything will be there eventually. It's just, it takes more time for you to read it, okay? So now that we know this, let's see how do we design cache. And in order to design cache, obviously the first question is, how do we measure the goodness of a cache, okay? The goodness of a cache is measured by the delay, right? Remember that this design that we had, what we had here was a data memory. And remember, we always told you that memory takes one cycle. That's all. But in reality, depending on where it goes, if it's in L1, it takes one cycle. If it's in level 2, it might take 20 cycles. If it's in L3, it might take hundreds of cycles. So you might actually end up stalling the processor many cycles depending on where your data is, right? So in order to improve the performance, not just your memory system performance, but the overall performance, you want to be able to provide the data back to the processor as fast as possible, okay? So the goal basically is that minimizing the access to the main memory. In other words, providing the data back to the CPU as fast as possible, okay? How do we measure that? We measure that through this formula called average access time, or AAT, okay? So the average access time is what we really care about. We want our average access time to the cache as minimum as possible. Ideally, we want to be this to be one cycle, okay? If it's one cycle, then we have what we had before, right? So we can access as fast as possible. We cannot go beyond one cycle. There's no point for it. But if I can access my cache in one cycle, then I'm good to go. So how do I measure this? I measure access time basically by these three metrics, okay? The average access time is hit time plus miss rate plus miss penalty, okay? So the way it works is this, that I need to search the cache for the data, okay? Regardless of whether this is a hit or miss, I need to pay this amount of time. This is what we call hit time. The time it takes for me to search through the cache, okay? If it's there, okay, if I find my data all the time, okay, my miss rate would be equal to 0. It means that the times that I have a miss is 0. So this part of the equation is gone. It means that my average access time is basically my hit time. So if I, for example, searching the cache takes only 1 cycle, then my average access time is 1 cycle. Okay? If my cache becomes bigger and bigger, the hit time unfortunately goes up just because of the technology. As a result, my average access time goes up. Okay? The reality, though, is that it's not always just the hit time. Not always your data going to be in your cache. This is what we call miss rate. That is, the amount of time we go to the cache, how many times the data is there, how many times it's not. That is what we call miss rate. Okay? So when we have a miss, then we need to go and grab the data from a lower layer. Okay? This is what we call miss penalty. The time it takes to grab the data if it's not in the cache, then we call that miss penalty. So the overall formula would be this, that average access time is equal to time to search. If it's there, great. If it's not, how many times it's not there? That's our miss penalty, miss rate, times how much time does it take for me to bring the data back to the cache? That's my miss penalty, okay? So if I have one level of cache and one main memory, this is how we're going to basically compute this, okay? That, for example, let's say my hit time for my cache is 2 cycles, right? My miss penalty, let's say for caches, you usually go really high. So like your hit rate is 90%. In other words, your miss rate is 10% miss rate. And then your miss penalty, as I told you before, typically is in order of hundreds and thousands of cycles, okay? So for example, for a system like this, you can quickly calculate what is my average access time, okay? So if my hit time is 2 cycles, 90% of the time I only have 2 cycles, but 10% of the time I have 10 cycles, what would be the final number? Anyone? 20? Why 20? So the way we're going to calculate this is based on this formula, right? So my hit time is 2 plus my miss rate is 10%, 0.10, 0.1, and my miss penalty is 100 cycles, okay? So that gives me what? 12, right? So my average access time in this system will be 12, which means that on the average, what I see from this system is 12 cycles. How can I improve this? I can improve this by 3 ways, right? So I either reduce this hit time. I mainly try to increase this significantly. So for example, if this was 99% or this was 1%, then this would have been 0.01, and this would have been 1, and then this would have been 3, right? So significant improvement, like 4x improvement if my miss rate from 90% became, my hit rate from 90% became 99%. So the design of the cache is all about these 3 metrics, okay? So for the rest of the lecture today, on Thursday and next week, we're going to talk about how we make these things better. Of course, the problem that we're going to face and the challenge that we're going to face is that unfortunately we have limited space in our cache, right? So we need to be able to very intelligently store data in my cache. I need to be very meticulous and very selective in terms of what do I store in my cache in order to optimize this, okay? And this is what goes under what we call cache management, okay? So what I store when I get rid of things, what do I replace it with, how should I kind of architect my cache, how should I address my cache, what should I use as a tag, and all those things is the art of designing a good cache and cache management. So we're going to go over and talk about those things, okay? One last thing I want to say before I let you guys go is how do we find and store data? Because the very first thing that we need to do in the cache is see whether the data is in the cache or not, right? So that's the first thing. And as I said, the time it takes for finding that is hit time. So I need to minimize that first. That's the first thing I need to do. Okay, so let's see how do I do that. So how do I store and find data? So what do we do to do that? And remember that basically what we need to do is the address is the indicator of my data, right? So the ID of my data is the address. We're assuming that every address is pointing to a byte, right? And we can store things in byte by byte in my memory. So my cache should kind of follow the same format. So the address comes, I need to be able to provide data, right? So what do we need to provide? We need to provide the actual value, right? But since not everything is stored in the cache, I also need to tell the request whether this was a cache hit or a cache miss. So it's kind of like what we're providing is two things. We first tell the CPU that whether we have the data or not. If we don't have the data, then the processor needs to go and grab it from the next stage, which is like either the main memory or level 2 or level 3. But if the data is there, I also need to provide the data. So the search problem becomes a two-step problem. The first step is providing an answer as such as yes or no, the data is there, or hit or miss. And the second step is that if the data is there, providing the data. If the data is not there, then of course there's nothing to do at that point. Okay? So the first question is that, okay, how much memory do I need if I have 32 bits data or PC or address? And if each unit is 1 byte, then I need to 32, 2 to the power of 32 times 1 byte. This will goes about 4 billion lines of memory. And as I said, caches are small in order of kilobytes, hundreds of kilobytes. So I cannot obviously store 400 billion lines of memory into my cache. I can only store 32,000 of it. So significantly less, okay? So what should I do? I need I need some form of a mechanism to kind of tell whether the data is there or not. So I need a mechanism to quickly check my cache and say that, yes, your data is here, here's the value, or the data is not there. Because remember, there are many, many times that the data is not going to be there, okay? And as I said, as you can see, the reality is that if this is your memory, okay, there will be many, many lines that are mapped to the same line in the cache, okay? So for example, in this case, I'm just using an arbitrary mapping, but you see that all the gray lines in your memory, these are different bytes in your memory, they're all mapped into the same cache. So there is some notion of overlapping between the data that exists in your cache, okay? So that's one thing that we need to be able to figure out. So once we have that, since for every single line there is multiple options, we need a mechanism to distinguish these options from each other, right? So if I store something in my cache, the question is, how do I know what did I store there, right? And this is where we're going to use the same story that we did for BTB. We're going to use tags. So essentially, we're not storing the data. Not only we store data, we also store the tag of that data so that we are able to distinguish which one is which. So not only I store this, whatever value that's stored here, I'm going to assign a tag. Let's say, for example, 0, 1, 2, and 3. And what I'm going to do is that I'm going to say that, oh, I'm going to store this value and tag 0, which means that this is the actual value that I'm storing, okay? So next time I'm going to explain how do we do the tagging and how do we store these and how do we structure the cache such that we can have a fast system. Remember that the idea is that we want to be able to have low hit rate, low miss rate, and very, very low average access time, okay? All right, see you guys later. Thank you.